Alright, hello and welcome back. My name is Cameron Kirk and this is video 13 on my series of videos on Verilog Development. And I think it's been a little bit of time since I've had my last Verilog dedicated video. That is because we did a lot of work on figuring out how to get the HPS, or the hard processor system. I always forget what HPS stands for. But the ARM core that's like dropped in the middle of this FPGA fabric. We wanted to figure out how we can use that to interface with a custom IP on our design, and we have since seen how to do that. So in today's video we're going to be making a 8-bit ALU. A ALU is a arithmetic and logic unit. And let's just do a quick Google search. ALU, arithmetic and logic unit. Basically this is like the brain of the CPU. People say that the CPU is the brain of the computer. Well, the ALU is actually the part that does the computing. And pretty much what you have here is, like, you know, the opcode gets decoded by the decoder, and then we're going to set the ALU to do some sort of operation. And it can take two operands, or maybe just you only use one operand and just ignore whatever's applied to the second operand. And it's going to output a result. So yeah, let me, let's see, what do I have open right now? I'm going to just show you the code, and then we're going to jump right in with implementing it. Surprisingly, implementing an ALU is very, very easy. I really should have cleaned up my windows before we started. Okay, so, oh yeah, I was working on how to get the analog digital converter working. I'm going to make a new folder in my DE10 Nano project folder. I'm going to call it, what did I call it? 8-bit ALU. 8-bit ALU. ALU live. There we go. And then I'm going to copy in under the downloadable CD, link is in the description if you don't have this. I'm going to copy in the golden reference design. Copy, and we're going to start to build this thing out. Okay, 8-bit ALU live, paste it in here. Excellent, and then we're going to go ahead and launch this project into Quartus. And let me get out of the way here. And then I believe it's going to ask me for an IP upgrade. And if so, I'm going to go ahead and pause the recording. But yeah, we're going to jump right in on this tutorial. I don't think it'll take too long. Also, check the video description for the link to the GitHub for this project. If you just want to jump straight into the Verilog code and you don't really want to see the walkthrough, keep in mind that that is in the description if you just want the code. It is really simple code. Okay, it looks like it's taking a minute to load here, but while that loads, let me show you. I'll grab from my previous attempt. It took me a few tries, and I'll get into why later. Okay, I'm just gonna grab these two things and put them, and then I'll show you their contents. And again, yeah, it's all on GitHub if you just want to have access to these files. So I'm gonna make two folders in the IP folder of our golden hardware reference design. Okay, it looks like Quartus finished loading, and it might ask you to upgrade, in which case just say yes, and then it might finish with an error. Don't worry about that. Go ahead and follow through with that. What I did was I saved the upgraded version into this folder. So where I downloaded the system CD, you can see it's been modified recently. And that's why it's not asking me to do that anymore. I am going to go into, well, before I do that, let's talk about the ALU code. So I'll get to this PIO64 in a second here. Under byte ALU, I'm going to open this up with code, and I'm just going to show you the code that we're working with. Again, it is all really simple. Like, it's surprisingly simple how short the Verilog code is to describe an ALU. But I'll talk you through how it works and show it to you. Alright, let's blow this up a little bit. Let's go one more. Okay. And I'll get this off my screen. Okay, so our module is called Simple ALU, and we can make instances of this ALU, as many as we want. And in terms of, okay, so here's our output, our result, operand A and B, and our control. So, control, we're only using 3 bits from control, and this is to select what operation we want to do in our always block here. And we have bit shifting. I believe this is like a rotate left, rotate right. We have an add with a carry, which I honestly don't think this was necessary, because I originally had a carry in, and then yeah, I ran into some problems. I had to simplify this a lot. So this isn't really necessary to have, but yeah, the code is in the description. We have a logical AND and a logical OR. So this is not bitwise, this is logical. And yeah, there's not much more to talk about. Everything, oh, the result is actually 9 bits wide. And that's because the way I made this project work is I used the instructions on this wonderful Zhangman DE10 Nano repository, their walkthrough demonstration of the simple hardware adder. This is basically going to be the exact same setup as the simple hardware adder, except we're just adding an extra PIO spot for the control register. So the simple hardware adder, if you haven't seen that, I already have a video walkthrough on how to set this one up. But you have A and B, 2 operands, and then they get added together in a full adder in parallel. And then there's 1 output. And so our ALU, it's going to be 2 operands A and B, just like the simple adder. There's going to be 1 result, just like the simple adder. And then 1 extra thing is we're going to have 1 more operand, and that's going to be our control operand. And the control operand is how we're going to select what operation we want our ALU to do. Okay, so with that out of the way, I'll go ahead and save this. I only removed a couple of spaces. I'm going to close this down. The code is really straightforward, really simple. We're going to go into QSys. And I hope I don't forget any steps. I think once QSys launches, I might have to pause the recording so that it can do its upgrade or whatever. I don't remember if that's going to be included. Let's take a look. Make sure my phone is muted. Yes, it is. Good deal. All right, we're going to load up the QSys file. And I'm going to pause the recording. We'll come back when this is done. Okay, so that finished loading, and did not require an upgrade. So we're just going to step through this simple adder, but we're going to make the small necessary changes to get the ALU Verilog code to work. So we're going to skip the initial project setup. We're not going to do any of this trimming down. Totally not necessary. We're going to go next. And then the simple adder module, we already have ours in our IP folder, so we're done with this page. This has no instructions on it, but it explains the Avalon bus. And yeah, one of the things I tried to do on my first couple of attempts was I tried to make the ALU 1 byte, and I tried to make each operand take 1 byte of memory. And what I found out, and then I tried to do 32 bits or 4 bytes of memory for each operand, but still only used the first byte. And that still didn't work, so I think I still have some learning to do on how this Avalon memory mapped bus works. Because apparently the only time I was able to get results that I expected to get was by doing exactly what is shown in this simple adder walkthrough. So hopefully I'll have a more detailed video on this bus in the future. But yeah, I still have some learning to do there. So we're going to roll with this setup, and they define their own custom PIO in and PIO out components. So let's go ahead and do that. This page has the code for PIO out. You can go on this GitHub, link is in the description to get this, and you just paste it into our IP folder here. So I've already done this. And I'm not even going to bother showing you because I've already done this. And it's all in modified, so it's all in there. And then this is what we need to do. So we're going to go into QSys, and we're going to make a new component up here. And it's going to be called PIO64 underscore out. Make sure I got that right. Let's do this. Get that out of the way. Oh, that did not work. Parallel I/O 64-bit output. Excellent. Okay, we're going to go into Files. We're going to add a file. We're going to go into IP folder, PIO64, and get our PIO64 out. We'll do the analyze synthesis file. Excellent. And then we go down to signals and interfaces. And we're going to rename Avalon slave 0 to PIO out, PIO64 out. Change the type to conduit. So this is now conduit. Give it a reset. And then change our PIO out. This will be export. Okay. Looking good. Reset input. And then on S0, give it a reset. Whoops. Oh, what did I do? Remove. Is that? Yeah, that's not supposed to be there. Give that a reset. Good deal. Now we're going to save it and hit finish. Now we do the input. And it's the same process. PIO64 in. See if I got that right. Yes, I did. Let's get our file in there. Add file. This time we're going to go into IP, and then we're going to go into PIO64, and then we're going to get this PIO64 in for input. Analyze. Okay, so this becomes PIO64 in with a reset and its conduit. This becomes export, and you have to type it in. Okay. And then S0 gets a reset. And that should be everything. Yep, so we're gonna save it, and we're gonna click finish. All right, now we're gonna move on to wiring the components. And we're gonna be using 3 outputs for the A operand, B operand, and control operand, and then 1 input. Now we're not going to add in another Avalon bridge, so don't follow along with these instructions. What we're going to do is, I believe one thing we have to do is right-click, edit our HPS0, and make sure that's on 64-bit, which it is, which is good. Go down to your bridge. Why do I keep scrolling past it? And then instead of this dot for S0, instead of this dot, which is the lightweight AXI master, we're going to use the heavyweight. So the one right above it, H2F AXI master. Check that one, uncheck this one. So it should look like that. Okay, and then let me see, do we edit anything in here? No, well, I think, let me just take a peek in here. Yeah, they changed that to 64. Okay, so let me hit cancel. Right click on your bridge 0 and change that to 64. Good deal. Finish. Okay, we're going to add in our outputs. We're going to get 3 of them. So I'll click finish. I'll get another one. I'll click finish. I'll get another one. I'll click finish. And then we're going to get 1 input. And click finish. And they're all going to get clock and reset. Okay. And then PIO0 will be our ALU A. And our next one is ALU B. And then this one is ALU CNTL. And this, we're setting these as exports. So we're putting these as exports so we can access them inside the design. This last one will be ALU result. Okay, now what else do we have to do? We have to connect them to the AXI master. Oh wait, we already did this, and now we're gonna do this. So we did this. Now S0 is going to bridge0.m. Okay. That one, that one, that one, and I believe that one as well. And the input, these are looking good. Okay, we have to give these all proper addresses. So A comes first, and then B will pick up where A ended, and control will pick up where B ended. So now we're going to hex 10, and then A will pick up where control ended. So we're going to hex 18. And I think that's everything. Yeah, so we're going to save this. I'm going to have to pause the recording in a minute here. We're going to start the generate HDL step. Click close, generate HDL, and generate. Okay, I'm going to pause the recording here and we'll come back when this is done. Okay, we are back and that is done. I believe we're good to go on there, so we're going to go ahead and click finish. And oh yeah, Cordis does this thing where it's like not responding. That's okay, I'll go to the next instructions. Actually, let me pause the recording until it comes back. Okay, it's back. I'm going to click OK on this. We're going to go into come on. Oh, yeah, because okay, hold on. Let me pause the recording. I need to restart Quartus. I think it's because I'm on version 17. I should really switch over to one of the newer versions. Okay, we're back. All right, so if we jump into files and on this first SoC system.v, we can see all of our wires are now created, 64 bits long. So that's looking good. Oh, we need to add remove project files on here. And we are going to click on the 3 dots over here and jump into IP and byte ALU and get this Verilog here. Click apply. Oof, it's going so slow. Guess I should have clicked OK. Alright, I guess I'm going to pause the recording until it comes back. Okay, we're back. And the moment I clicked pause is when it caught back up. Okay, so that is now included in our project. We're going to go into this top level entity and scroll down until we see reg wire declarations. I'm just going to steal this guy and come down here. And we need a 63 down to 0 wire. We'll call it ALU wire. I'll call it ALU A wire. I think I made too many. Yeah, I did. Okay. By the way, if you're wondering how I'm selecting the whole line, I'm pushing the end key on your keyboard, the end key that takes you to the end, holding down shift and then pushing the home key, and that highlights the whole thing. You can also just push the home key to go to the start of the line. I like that a lot more. It feels fast. Okay, so we're going to do B, CNTL, and results. There we go. And then we need to instantiate our simple ALU. So simple ALU, my ALU, what is it? Parentheses, semicolon. I'm pretty sure I'm doing this right. But what I'm doing is from these instructions right here, they're instantiating it like that. Okay, so let's jump into the ALU code and grab the port map or the port listing. Nice and simple, that's all there is to it. Go back into Quartus and put it in here. I'm going to give this a tab. Just enter, enter, enter. All of these need to begin with a period. There we go, and they all need open and close parentheses like that. Okay, so we have 64 bits here, but we're actually only going to be using 8 bits. If we take a look at the Verilog code, input is only expecting 8 bits, so we're only going to give it 8 bits from the 64 bits. So for results, we're going to give it 7 down to 0. And then for, actually this gets 8 down to 0. Whoa, go back. 8. That's because we gave it 8 down to 0. Probably not necessary. A wire goes here, and this will be 7 down to 0. Now I'm holding down shift and using the arrow keys to select that. These guys are all going to get 8 bits like that. Save it. Let's go back to the instructions. So we have our simple adder added in here, separated by commas, ending with a semicolon. The other day I forgot that. I have it. Okay, now in here, this is where we are going to map up these guys. So go ahead and highlight all of that, copy it, paste it in here. I'm going to hold down the end key and backspace those comments. Pretty sure it was complaining to me the other day because of that, which was interesting. And then or maybe it was something else, I don't remember. Get rid of output wire, get rid of the length as well, and put a dot in front of it. So, oops. Like that. Give all of these parentheses. Okay, and then on this one we don't have to specify, we can just give it the whole thing. So we're just going to give it the whole wire vector. Right, let's double check on that. Yeah, just like that. All right, save it. And there's the code, and now we compile, right? Yep, now we compile. So I'm going to go ahead and click this blue play button to start compilation. And I'm going to pause the recording, and we will come back when this is done. All right, we are back, and that is all done. I just hope that worked, because that was a long time to compile. Hopefully it wasn't as long for you. We're going to go up to File, and then we're going to go to Convert Programming File. Select Raw Binary File, select this SOF, click Add File. Inside your output, select this SOF, and click Generate. Oh, I wanted to rename it. That's okay, we'll do that after it's done. Okay, so that finished. And inside our directory here for our live demo, there it is. That's why I wanted to rename it. I'm still going to rename it. This will be Simple ALU Live. Okay, there it is. So I'm going to hold down Shift and right click on the folder and open PowerShell. Oh, we cannot continue any further because we need to actually switch over to the tabletop and get our USB connected to the UART USB port at the bottom next to the Ethernet. And then before I supply power to the board, we are going to open up a serial connection software like PuTTY. And I know that it's going to be on COM3, 115, 200 is the baud rate. And once I supply power to the board, it's going to come to life. Oh, actually, let me terminate that session. That's fine, it's still going to keep booting. I actually had a pre-save that had the larger font size that I like. Good deal. So we're just going to wait for this to come up, and once it hits the login screen, that means we can SCP our project to it. I'm going to type out SIMP and then hit tab. It's going to auto-complete that for me. I'm going to send it to root at 192.168.0.62 tilde, colon tilde. Password is root. And there it goes. So now we'll get logged in over here. And by the way, this only worked because I saw that I was at the login screen. Okay, we now have this simple ALU live. We're going to type mount /dev/mmc. Whoops, I have too many slashes. P1 FAT. So I have a folder called FAT, and we're going to mount it to that. So now we have this stuff in here. And then what we're going to do is we're going to CP simple ALU RBF into FAT SoC _ system RBF. And then we're also going to move this RBF away into my FPGA binaries. Sorry. We're going to move simple into FPGA binaries, simple ALU live.rbf. So now that is filed away, and we're going to do a reboot so that it will flash our design to the FPGA. Cool, so hopefully that is good. I am now going to switch over to our cross-compiler development environment. Let me close out of PowerShell. And let's go to a larger font size on here. I'm thinking 24. Clear ls. Alright, I'm going to go into our DE10 nano working directory. And I'm going to make dir, and we're going to have simple ALU live. Okay, and then I'm actually going to, if I do an ls on byte ALU, I'm actually going to copy the code that we're going to be using. If you want to, I'm going to walk through the code, but I'm not going to spend time typing it out. If you want access to the code for this C program, that is also going to be available on the GitHub. So keep a lookout for that. And the purpose of this C program is to supply operands to our FPGA IP. So we're going to supply an A operand and a B operand. Actually, let me copy this over and then we'll talk about it. So I'm going to cp from byte ALU myprog.c, and we're going to send it into simple adder live myprog.c. And then we're going to cd into simple adder live. Wait. That kind of stinks. It just blew. Oh no, we're good. Okay, let me fix this. I sent it to the wrong folder. I guess I'll call it byte. I can't. Simple ALU. Okay. And I'll do a code dot. Okay, so let's talk through this C code here. This C code is basically the same code that's offered on here, but modified to work with our setup. So all the way at the bottom here, there's the full program code, and then we've modified it. So we're not doing this. We've added a struct. Oh yeah, so I've done a previous video that talks about how to upgrade that code. We're actually going to be using a struct for mapping the bytes. This isn't necessary. We'll take that off. We have our bridge here. The span is 20, which is works out to be however many. 64 bits is 8 bytes. 8 times 4 is 32, or a hex 20. So that's our span. And then we're making a pointer, an ALU pointer. And then we're casting the pointer we get from mmap into a ALU. And then we're parsing our argvs to set these values. And then I just have this real simple print statement here at the bottom. The other thing you're going to need is make sure you have your exports already configured. So I'm going to go ahead and do this. Good deal. And then we're going to compile it using the compile command on here. Okay, so that compiled without errors. Let me move my prog to simple ALU live. Okay, we're going to SCP simple ALU live to root at 192.168.0.62 colon tilde root, and off it goes. Let's come over here. And there it is. We're going to do a / simple ALU live, and it wants to know. Oh yeah, so for this code, I was going to go through the work of decoding commands, but I'll leave that to the viewer. For now, I'm just going to take a number for which operation you want. And in order to decode this, you need to look at the Verilog code, what we defined in hardware. So 0 is a logical AND. So if we have 0 and 0, and we're going to do logical AND, we should get 0. I should have done a better one to start to make sure it's actually working. So 3, that's a binary 3, or decimal 3 in binary, is add. So we're going to add 0 plus 0. Let's add 1 plus 1. The result is 2. So since these are outputs, we can't actually read these. So it's a little bit redundant to have these printing out. I probably should have corrected that before compiling it. And it's actually not too much work to change that. So let's come back over here. We can only read from our result. That is our only one that has the PIO64 in. So I'm going to save that. We're just going to call that compile command again. I should have changed the compile command, but I have to do this again. And then we're going to send this off with root. Come back over here, clear ls 2. Oh, and I also have it print out the hexadecimal value. But 1 plus 1 is 2. Let's do something bigger. 100 plus 15, 115. Let's do... So because we're using a byte... Oh, yeah. We're using a byte and a bit. So we can go past 255 in the result. But we cannot go past 255 in the operand. So if I clear this, clear this, if we do 255 plus 0, add them together, we get 255. If I set this to 256, I'm expecting it. Oh, so we had overflow. So there should be a most significant bit there. Let's do this. This is pretty fun to play around with. So 256, you can see we've zeroed out our bytes, and there's a carry bit here, but our operand doesn't support that. So just interesting thing to think about. 255 is the max you can put for a byte, and 255 for this other operand. I also leave it to the viewer to think about how you would expand this to be more than just 8 bits or a byte. Very, very easy to do, and in fact I plan on doing that in a future video if people are... I'm actually interested in doing something really crazy for like a super crazy, I don't know, 128-bit, 256-bit, 512-bit ALU. That would be interesting. What else can we look at? Okay, so if we go back to the ALU code, A4 is subtract. So simple ALU, 3 minus 1 in subtract mode gives us a 2. So 3 minus 1 is 2. So that works. Okay, so we've been really hitting the adder a lot. Let's hit this logical and it's not bitwise and, it's logical and. So that is mode 0. So if I put this in mode 0, we get a true. And basically what this is saying is, oh, and then if we do 3 and 0, we get a 0. So it's not doing a bit by bit and putting the result here. it's checking to see, is there something in this operand and is there something in this operand? True, then 1. False, then 0. So we can do 0, 255. We get a 0. And if we have 255 and 1, we get a 1. So that's the and then now we have or on the next one. So have both of them, and then just one of them, and then just the other one. And that's all true, but when they're both 0, it's a 0. So that's cool. This is bit shifting, so these are things that you might want your CPU to be able to do. We also have subtracting, we already saw that, and we have bit shifting. Oh, this is rotate. This is rotate. So the top 7 bits are moved to the bottom bit is moved around. Sometimes that's helpful. We can, so what is this, 2, mode 2. And it only cares about this A operand, so the first operand here. So if we have a 1, that becomes 128. If we have a 128, it becomes a 64. If we have a 64, it becomes a 32. So there's like rotation going on. I don't know. It's been too long since I've had to do a rotate to figure something out. It means it's one of the many pleasures of life, though. Yeah, I think that just about does it for this video. I hope you enjoyed this. I hope you found it interesting. I think it's awesome that this is working. I really wanted to try and make the bus only use 1 byte of memory. So you write to a byte, write to a byte, read from a byte. But I couldn't get that working. I guess one other thing that would be interesting is adding a multiplier in there and having a multiplier mode. But yeah, so this is sort of a proof of concept that we're not just limited to a combinational parallel adder, like a full adder. We can actually hook up whatever we want to the HPS and we could do really complicated designs and simply print our results and read the results right here from Debian Linux, and I think that is super awesome. So this was a really satisfying video to make. Thank you for watching if you made it to the end, and if you were able to get the same results that I did, feel free to leave a comment below, and I will see you in the next one. Take care. Bye-bye.